Close your eyes for a moment and imagine this scene with me. It's July 1st, 2025. The summer night is quiet over the Atacama Desert in Chile, one of the driest places on Earth. Most of the world is asleep. But high on a mountain ridge, a robotic telescope named Atlas, the Asteroid Terrestrial Impact Last Alert System, is wide awake, methodically scanning the heavens. It's doing what it does every clear night, taking pictures of the sky, comparing them to previous images, looking for anything that moves. And then, buried in the digital data of that night's observations, the telescope's software detects something, a faint dot of light, moving. But here's what makes the hair on the back of your neck stand up. This object isn't moving like it should. It's not following the predictable patterns of the asteroids and comets that call our solar system home. This thing is moving fast, too fast, and it's heading in the wrong direction. Within hours, astronomers around the world would realize what they were looking at. A visitor. Not from Mars, not from the asteroid belt, not from the distant Oort cloud at the edge of our solar system. No, this traveller came from somewhere else entirely, from the space between the stars, from another planetary system, orbiting another sun, in another part of our galaxy. They named it 3I, Atlas. The 3I means it's the third confirmed interstellar object we've ever detected passing through our cosmic neighbourhood. And over the following months, as the world's most powerful telescopes turned their attention to this wanderer, something became clear. 3I Atlas isn't just unusual, it's weird. It's changing colours. It's accelerating in ways that make some scientists scratch their heads in confusion. And it arrived on a trajectory that, according to some calculations, is so statistically improbable that it's raised eyebrows in the scientific community. Now, before your imagination drifts toward little green men and flying saucers, let's take a breath. What astronomers saw that night wasn't fantasy. It was something far more compelling. A traveller from another star, quietly threading its way through our solar system. The internet is absolutely drowning in sensational headlines about 3I Atlas. Alien probe. Some scream, NASA cover-up. Others shout. The government is hiding the truth. And you know what? 99% of it is complete garbage. Clickbait. Fear-mongering. Wild speculation based on misunderstanding, or worse, deliberate distortion of what the science actually says. So here's what we're going to do instead. We're going to follow 3I Atlas through every stage of its story, what it is, how we found it, and what its brief, brilliant passage reveals about our place in the cosmos. We'll explore the real mystery, one far more fascinating than any alien conspiracy, and uncover why this interstellar visitor continues to challenge even the sharpest scientific minds. We're going to trace its journey across billions of miles and possibly billions of years. We're going to dive into the cutting-edge observations being made by the Hubble Space Telescope, the James Webb Space Telescope, and dozens of observatories around the world. We're going to understand the physics, the chemistry, the orbital mechanics, and yes, even the controversies. And by the time we're done, you're going to understand why 3I Atlas is genuinely important, not because it might be aliens, but because it's giving us an unprecedented window into how planetary systems form around other stars, how material is distributed throughout our galaxy, and what secrets lie in the cold darkness between the stars. So buckle up, turn off your phone notifications, get comfortable, because we're about to embark on one of the most fascinating cosmic detective stories of the 21st century. Let me take you back to that moment in early July 2025, and let me explain just how remarkable it is that we detected 3I Atlas at all. You see, space is incomprehensibly vast. To put it in perspective, if Earth were the size of a grain of sand, the nearest star system, Alpha Centauri, would be about 40 kilometers away. And 3I Atlas didn't come from Alpha Centauri. It probably came from much, much farther. The Atlas system that discovered it isn't looking for interstellar visitors. It's part of NASA's Planetary Defense Program, designed to find potentially dangerous asteroids that might threaten Earth. It consists of 4 robotic telescopes stationed around the world, 2 in Hawaii, 1 in Chile, and 1 in South Africa. Each telescope scans huge swaths of sky every single night, taking multiple images of the same regions and using computer algorithms to detect anything that moves between frames. On the night of July 1st, 2025, the Chilean Atlas telescope captured 4 separate images of a faint object between 5:15 a.m. and 6:20 a.m. local time. The object appeared at coordinates 18 hours 0, 7 minutes 27.68 seconds in right ascension and negative 18 degrees 41 minutes 40.2 seconds in declination. For those of you tracking along with your star charts, at discovery, it had an apparent magnitude of about 17.5, far too faint to see with the naked eye or even most amateur telescopes. You'd need a fairly substantial telescope and a good camera to spot it. The software that analyzes Atlas data flagged this object as potentially interesting. Its motion was unusual. It was moving at an angle and speed that didn't match the expected behavior of main belt asteroids or typical comets. The discovery was immediately reported to the Minor Planet Center at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, the official clearinghouse for all observations of asteroids and comets. Within hours, something extraordinary happened. Astronomers around the world started looking at archival data, images taken in previous weeks that hadn't been carefully analysed yet. They found 3I Atlas in older images. The comet had actually been photographed as early as June 14, 2025, by the Zwicky Transient Facility at Palomar Observatory in California. It was there in the data all along, but nobody had noticed it because it was so faint and because nobody was specifically looking for it. This is actually incredibly important. Those pre-discovery observations extended the baseline of observations back nearly 3 weeks, which dramatically improved the precision with which scientists could calculate the object's orbit. And what that orbit revealed was absolutely stunning. Let me explain what makes an orbit interstellar, because this is crucial to understanding the story. Every object orbiting the Sun follows a path determined by the Sun's gravity and the object's velocity. If you could measure an object's orbit precisely enough, you can calculate something called its orbital eccentricity. This is a number that tells you the shape of the orbit. An eccentricity of 0 means a perfect circle. An eccentricity between 0 and 1 means an ellipse, like most planets. An eccentricity of exactly 1 means a parabola. The object is travelling at exactly the Sun's escape velocity. An eccentricity greater than 1 means a hyperbola. The object is travelling faster than the escape velocity, meaning it's not bound to the Sun and will eventually leave the solar system. When scientists calculated 3I Atlas's eccentricity, they got a number around 6.1 to 6.2. That's way over 1. This object is moving so fast that the Sun's gravity cannot hold it. It's just passing through, and once it leaves, it will never return. But here's what sealed the deal. When you trace a hyperbolic orbit backward in time, you can determine where the object came from. But objects from our solar system, even those on highly eccentric orbits, when you trace them back, they still came from somewhere within the Sun's gravitational influence. But when scientists traced 3I Atlas backward, they found it came from outside, from interstellar space, from the galaxy at large. On July 2nd, 2025, the Minor Planet Center made it official. They announced that 3I Atlas was confirmed as an interstellar object and gave it the designation 3I, the third confirmed interstellar visitor to our solar system. After 1I, Oumuamua in 2017 and 2I, Borisov in 2019. I want you to imagine what happened next, because it's a beautiful example of how science works when something exciting happens. Within minutes of the announcement, astronomers worldwide started scrambling for telescope time. You have to understand, interstellar objects are rare, incredibly rare. We've only confirmed 3 in all of human history, and 2 of those were discovered in the last 8 years. Every minute counts, because these objects are moving at tens of thousands of miles per hour, and soon they'll be too far away to study effectively. David Jewett and Jane Liu, 2 legendary planetary scientists who've been studying comets for decades, immediately requested urgent observations with the Nordic Optical Telescope in Spain. When their images came through on July 2nd, they saw something that filled them with excitement. 3I Atlas wasn't just a point of light. It had a diffuse, fuzzy appearance, what astronomers call a coma. This meant the object was active. It was releasing gas and dust as it warmed up approaching the Sunday. This was important because the first interstellar visitor, Oumuamua, showed no obvious cometary activity. It looked more like an asteroid, which led to years of debate about what it actually was. But 3I Atlas? From the very beginning, it looked like a comet, a classic dirty snowball from space. At the Instituto de Astrofísica de Canarias in Spain, a team using the 2-meter twin telescope at Teide Observatory confirmed the activity on the same day. In Arizona, astronomers at Lowell Observatory trained their telescope on the visitor. In Chile, the massive 8.2-meter Gemini South telescope got into the act. Perhaps most excitingly, within days, NASA's Hubble Space Telescope was retargeted to observe 3I Atlas, the space-based observatory, free from the blurring effects of Earth's atmosphere, could see details that ground-based telescopes couldn't match. Now, before we go any further, I need to explain why 3I Atlas is particularly special compared to the previous interstellar visitors. When Oumuamua was discovered in October 2017, it was already on its way out of the solar system. It had passed its closest point to the Sun perihelion a month before it was discovered. Astronomers only had about 80 days to study it before it became too faint and too far away to observe. It was like catching a glimpse of a mysterious stranger already walking away down the street. 2I Borisov, discovered in August 2019, was better. It was spotted about 3 months before its perihelion passage in December 2019, giving scientists several months to study it on the way in and several more months as it left. But even then, the observation window was limited. 3I Atlas is different. It was discovered in early July 2025, a full 4 months before its perihelion passage on October 29, 2025. This means scientists had the entire inbound journey to study how the comet changed as it approached the Sunday. They could watch it warm up, become more active, and evolve in real time. It's like meeting someone at the start of a journey rather than seeing them rush past. Even better, after perihelion, 3I Atlas will make its closest approach to Earth on December 19, 2025, at a distance of about 270 million kilometers. This gives scientists another opportunity for detailed observations as it heads back out into the cold. This extended observation window is a gift to science. Every additional day of observations provides more data, more precision in orbit determination, more opportunities to measure the comet's composition, and more chances to solve the mysteries it presents. Let me tell you about the naming, because there's actually a lot packed into those simple characters. 3I Atlas. The 3I part we've covered, it's the third interstellar object. The I officially stands for interstellar in the designation system created by the International Astronomical Union. Atlas honours the survey system that discovered it, the Asteroid Terrestrial Impact Last Alert System. It's tradition in astronomy to name comets after their discoverers, and since Atlas is a robotic survey rather than an individual person, the survey itself gets the honour. But if you want to get technical, the object also has a more formal designation, C 2025 N1 Atlas. The C means it's a comet, as opposed to an asteroid. The 2025 N1 follows a system where 2025 is the year of discovery. N indicates it was discovered in the first half of July, each half month gets a letter, and 1 means it was the first comet discovered in that period. This might seem dry, but compare it to the names of the previous interstellar visitors, and you'll see something interesting. The first one, Oumuamua, is a Hawaiian word meaning roughly scout, or messenger from afar arriving first. It's poetic, evocative, mysterious. The second, Borisov, is named after its discoverer, amateur astronomer Gennady Borisov. And now we have Atlas, named after a robotic system. There's something almost symbolic in that progression. The first interstellar visitor got a mystical name because it was so unprecedented and strange. The second got a personal name because we were starting to understand these objects better. And the third gets a technical name. Because we're entering an era where discovering these visitors might become routine, the mystery is becoming science. So what did those first observations reveal? First, the basics. At discovery, 3I Atlas was about 670 million kilometers from the Sun, somewhere between the orbits of Mars and Jupiter. It was inbound, heading toward the inner solar system at a speed of about 221,000 kilometers per hour, 137,000 miles per hour, relative to the Sunday. That's about 61 kilometers per second, or roughly 0.02% the speed of light. Fast by any human standard, but actually on the slower end for interstellar objects. The comet appeared slightly reddish in color, with color measurements suggesting it was similar to many comets in our own solar system. This reddish tint comes from organic compounds called tholins, complex molecules that form when simpler carbon-based compounds are exposed to ultraviolet light and cosmic rays over long periods. The red color told scientists that 3I Atlas had spent a long time in space, long enough for these compounds to form on its surface. The coma, that fuzzy cloud surrounding the nucleus, was already apparent in those first images. This meant the comet was already warm enough for ices to sublimate, turn directly from solid to gas. Given how far it still was from the Sun, this suggested the presence of very volatile materials, substances that vaporize at extremely low temperatures, like carbon monoxide or carbon dioxide. And here's something fascinating. Even in those very early observations, scientists could see hints of a faint tail. It wasn't dramatic or obvious, but careful image processing revealed a slight elongation pointing away from the Sunday. This is exactly what you'd expect from a comet. Solar radiation pressure pushing small dust particles away, creating that iconic tail. Everything in those first few days suggested 3I Atlas was behaving like a normal comet. It had all the expected features. But, as we're about to see, normal wouldn't last long. Before we dive deeper into 3I Atlas's story, I need to take you back to 2017, because you can't understand the third interstellar visitor without understanding the first. On October 19th, 2017, the Pan-STARRS 1 telescope in Hawaii spotted something extraordinary. At first, it looked like a faint asteroid, just another dot of light among millions. But when astronomer Rob Werrick calculated its trajectory, he realized something was wrong. This object was moving too fast. Its orbital eccentricity was around 1.2, clearly hyperbolic. They named it Oumuamua, and for the next few weeks, telescopes around the world observed it intensely before it faded from view. And what they found was weird. First, Oumuamua varied dramatically in brightness as it rotated, suggesting it was highly elongated, perhaps 10 times longer than it was wide. Nothing in our solar system has that extreme a shape. It looked like a cosmic cigar, or in some interpretations, a pancake viewed edge-on. Second, it showed no obvious signs of cometary activity. No coma, no tail, no detectable gas or dust. It looked like a bare rock tumbling through space. Third, and this is where things got really interesting, careful measurements by the Hubble Space Telescope showed that Oumuamua was accelerating faster than gravity alone could explain. It was experiencing some kind of non-gravitational force pushing it away from the Sunday. For a comet, this would be totally normal. Cometary outgassing creates a rocket effect that can push the comet around. But Oumuamua showed no visible outgassing. So what was pushing it? Scientists proposed various explanations. Maybe it was venting gas that we couldn't detect. Perhaps transparent hydrogen. Maybe it was made of nitrogen ice like Pluto's surface, and that nitrogen was sublimating. Maybe it was covered in a layer of organic compounds formed by billions of years of cosmic ray bombardment. And then, Harvard astronomer Avi Loeb published a paper suggesting we shouldn't rule out the possibility that Oumuamua was artificial, a light sail or probe from an extraterrestrial civilization. This sparked enormous controversy. Most scientists thought the natural explanations were far more likely, but Loeb's suggestion captured public imagination and made Oumuamua a household name. The key point is this. Oumuamua was weird enough that even natural explanations required some unusual physics or composition. It didn't fit neatly into any category we knew. Fast forward to August 30th, 2019. Amateur astronomer Gennady Borisov, using a 65-centimeter telescope he built himself at the Margot Observatory in Crimea, discovered what he thought was a comet. Within 2 weeks, Enough observations had accumulated to prove it was on a hyperbolic trajectory. The second interstellar object had arrived, but 2I, Borisov, was different from Oumuamua in almost every way. From the moment it was discovered, it looked like a classic comet. It had a bright coma, it developed a beautiful tail, and spectroscopic observations detected cyanide CN molecules, a common signature of cometary activity. The Hubble Space Telescope captured stunning images showing it looked almost identical to comets from our own solar system. Scientists measured its composition and found it was rich in carbon monoxide CO and carbon dioxide CO2, similar to comets that formed in the outer regions of our own solar system. Its colour, its activity level, its dust production, everything was familiar. Well, almost everything. Detailed analysis showed that 2I, Borisov, had some unusual properties. Its polarization signature was higher than typical solar system comets, suggesting its dust had different properties. The ratio of carbon monoxide to water was unusually high, and it appeared to be one of the most pristine comets ever observed, meaning it probably never passed close to a star before entering our solar system, so its surface hadn't been heavily processed by solar heating. But the key point is, 2I, Borisov, behaved like a comet. It fit into our understanding of how these objects should work. After the weirdness of Oumuamua, 2I, Borisov was almost reassuringly normal. Now, here's a question that probably occurred to you. If we've only seen 3 interstellar objects ever, does that mean they're incredibly rare? The answer is fascinating. They're not rare at all. In fact, scientists estimate that at any given moment, there are probably 10,000 Oumuamua-sized objects within Neptune's orbit. That's right, 10,000 interstellar visitors inside our solar system right now. So why have we only detected 3? Simply put, they're incredibly hard to spot. Think about it. These objects are small, probably a few hundred meters to a few kilometers across. They're dark. They don't produce much of their own light. They're moving fast, so they're only co's in the inner solar system briefly. And they're relatively far away. It's like trying to spot a charcoal briquette being thrown across a football stadium at night. Until recently, we didn't have telescopes powerful enough to detect these faint, fast-moving objects. The Pan-STARRS telescope that found Oumuamua only became fully operational in 2014. Atlas started operations in 2015. These automated survey systems, which photograph huge areas of sky night after night and use computers to detect anything that moves, are revolutionizing our ability to find these interstellar interlopers. And it's about to get even better. The Vera Rubin Observatory in Chile, which began operations in 2025, will be able to photograph the entire visible sky every few nights with unprecedented sensitivity. Scientists predict it could discover dozens to hundreds of interstellar objects per year once it's fully operational. In other words, we're transitioning from an era where interstellar visitors are strange, rare events to an era where studying them becomes a regular field of astronomy. Let's zoom out and think about where these objects come from, because this connects to one of the most fundamental processes in astronomy: planetary system formation and evolution. When stars form from clouds of gas and dust, they're typically surrounded by disks of leftover material, protoplanetary disks. Within these disks, dust grains stick together to form pebbles. Pebbles accumulate into boulders. Boulders merge into planetesimals, objects kilometers across, and planetesimals eventually grow into planets. But this process is messy and violent. As planets grow, especially giant planets like Jupiter and Saturn, their powerful gravity stirs up everything around them. They scatter smaller objects, some inward toward the star, some outward toward the outer reaches of the system. Some of these scattered objects get flung out of the planetary system entirely when a small object like an asteroid or comet has a close encounter with a massive planet. The planet's gravity can give it such a huge velocity boost that it exceeds the star's escape velocity. The object is ejected, cast out into interstellar space to wander the galaxy. Our own solar system has done this. Jupiter, in its youth, probably ejected countless asteroids and comets. In fact, models suggest that the early solar system ejected several Earth masses worth of material. That's millions upon millions of objects, ranging from pebbles to Pluto-sized bodies. Every planetary system probably does this, which means interstellar space is filled with the cast-off debris of planetary formation from billions of star systems throughout the galaxy. These wanderers drift through the dark for millions or billions of years until, occasionally, they pass through another star system. Some scientists estimate there might be 10 to the power of 26. That's 1 followed by 26 zeros. Interstellar objects in the Milky Way galaxy, with masses greater than 1 kilogram. That's an incomprehensibly huge number. Interstellar space isn't empty. It's actually teeming with these lonely wanderers. Let me tell you about one of the most important discoveries in planetary science over the last few decades, because it's directly relevant to understanding where objects like 3I Atlas come from. Astronomers used to think that planets formed in their current orbits and basically stayed there. The terrestrial planets, Mercury, Venus, Earth, Mars, formed close to the Sun where it was warm. The gas giants, Jupiter, Saturn, formed farther out where it was cold enough for ices to condense, and they had enough material to grow huge. The ice giants, Uranus, Neptune, formed even farther out in the cold, dark regions. But that simple picture is wrong. We now know that planets migrate. They change their orbits over time, sometimes dramatically. Here's how it works. Imagine a young Jupiter forming in a disk of gas and dust. The planet's gravity creates waves in the disk, kind of like how a boat creates waves in water. These waves carry angular momentum, the physics quantity related to rotation. If the waves predominantly carry angular momentum away from the planet loses angular momentum and spirals inward toward the star. If waves carry angular momentum toward the planet, it spirals outward. The specifics depend on the planet's mass, the disk's properties, and complicated orbital mechanics. But the key point is, planets don't stay put. They wander. In our solar system, there's strong evidence that the giant planets underwent massive migrations early in the solar system's history. According to a model called the Nice model, named after the French city where it was developed, Jupiter formed farther from the Sun than it is today, and Neptune formed closer. Through a complex dance of gravitational interactions, Jupiter migrated inward while Neptune was flung outward. This migration was catastrophic for smaller objects in the system. As the giant planets moved, they scattered planetesimals by the billions. Some crashed into the inner planets, creating impact craters we can still see on the Moon and Mars. Some were flung into the distant Kuiper Belt or Oort cloud, and some, perhaps millions of them, were ejected from the solar system entirely. 3I Atlas might be one of these ejected objects. Billions of years ago, in a planetary system somewhere else in the galaxy, a giant planet might have had a close encounter with the young comet that would become 3I Atlas. That encounter accelerated the comet to escape velocity, sending it on an eons-long journey through interstellar space until, by pure chance, it encountered our Sunday. Alright, let's talk about one of the most powerful tools in modern astronomy, spectroscopy. This is how we figure out what things in space are made of without ever having to go there and collect a sample. Here's the basic idea, and I promise I'll make this intuitive. Every chemical element and molecule has a unique fingerprint in light. When atoms or molecules absorb or emit light, they do so at very specific wavelengths that depend on their quantum mechanical structure. Hydrogen absorbs and emits light at different wavelengths than oxygen, which is different from carbon, which is different from iron, and so on. When you pass light through a prism, or a diffraction grating a piece of glass with thousands of tiny parallel lines etched into it, it splits the light into its component wavelengths, creating a spectrum. If you look at that spectrum carefully, you'll see dark lines where specific wavelengths have been absorbed by atoms or molecules in the light's path, and bright lines where specific wavelengths have been emitted. By analysing these spectral fingerprints, astronomers can determine the chemical composition of distant objects. We use this technique to analyse stars, galaxies, planets, and, yes, comets. When scientists turned spectrographs toward 3I Atlas, they were essentially asking, what is this thing made of, and what does that tell us about where it came from? On August 6, 2025, the James Webb Space Telescope, humanity's most powerful space observatory, pointed its near-infrared spectrograph toward 3I Atlas. The The telescope collected light for several hours, building up enough signal to create a detailed spectrum. When the data came back and researchers analysed it, they found something remarkable. 3I Atlas is absolutely dominated by carbon dioxide, CO2. Now let me explain why this is significant. Most comets in our solar system are primarily water ice, with smaller amounts of other ices mixed in: carbon monoxide, carbon dioxide, methane, ammonia, and so on. When we measure the relative abundance of these different molecules, we typically find that water is by far the most abundant. But 3I Atlas? Its carbon dioxide to water ratio is one of the highest ever measured in a comet. It's not a water ice comet with some carbon dioxide mixed in. It's more like a carbon dioxide comet with some water mixed in. This immediately tells us something profound about where 3I Atlas formed. Let me explain the physics. In a protoplanetary disk around a young star, different ices condense at different distances from the star, depending on temperature. Close to the star where it's warm, no ices can form. Everything is either molten or vaporized. Farther out, where temperatures drop below 273 Kelvin, 0 degrees Celsius, water ice can condense. This distance is called the snow line or frost line, but different molecules have different condensation temperatures. Water ice is relatively stable and can exist at warmer temperatures. Carbon dioxide ice, on the other hand, requires much colder conditions. In our solar system, CO2 ice is stable at temperatures below about 195 Kelvin, negative 78 degrees Celsius. To reach such cold temperatures, you need to be quite far from the Sun, roughly 5 to 10 astronomical units, AU or more, depending on the specific conditions. The fact that 3I Atlas is so rich in carbon dioxide suggests it formed far from its parent star, well beyond that star's CO2 ice line, in the cold outer reaches of its home planetary system. It's a deep freeze object, a relic from the distant periphery of another star's family. If the carbon dioxide discovery was surprising, what came next was downright shocking. On August 21st, 2025, astronomers using the Very Large Telescope in Chile were analysing high-resolution spectra of 3I Atlas when they detected something completely unexpected: nickel vapor. Let me explain why this is so weird. Nickel is a metal. Its melting point is 1,455 degrees Celsius, 2,651 degrees Fahrenheit. For nickel to exist as a vapor, a gas, it needs to be heated to over 2,900 degrees Celsius, 5,250 degrees Fahrenheit. That's hot enough to melt iron and steel. But 3I Atlas, when the nickel was detected, was nearly 4 astronomical units from the Sun, almost 4 times farther than Earth. At that distance, temperatures are absolutely frigid, probably around negative 200 degrees Celsius, negative 328 degrees Fahrenheit, or colder. At such temperatures, nickel should be frozen solid, locked into the comet's rocky components. So how on Earth, or rather, how in space, is there nickel vapor around a comet at such cold temperatures? The research team, led by Rohan Rahatgaonkar and Thomas Puzia, was puzzled. It was pretty clear that it was nickel, Dr. Puzia told reporters. So it was super exciting. But exciting also meant mysterious. Here are the leading theories. Theory 1. Cosmic ray processing. For billions of years, 3I Atlas wandered through interstellar space. During that time, it was continuously bombarded by galactic cosmic rays, high-energy particles, mostly protons, flying through the galaxy at near light speeds. When these cosmic rays slam into the comet's surface, they deposit enormous amounts of energy. This energy can break chemical bonds, create new molecules, and fundamentally alter the structure of the ice and rock. Over billions of years, this cosmic ray bombardment creates an irradiated crust on the comet's surface. Some scientists think this irradiated crust might contain nickel in a form that can release vapor at much lower temperatures than pure nickel metal. Perhaps the nickel is in some exotic chemical compound that's more volatile, or perhaps the radiation damage created tiny pockets of nickel that can sublime at lower temperatures. Theory 2. Micrometeorite impacts. Even in interstellar space, 3I Atlas wasn't completely alone. Interstellar dust particles, microscopic grains drifting through space, would occasionally collide with the comet. At the speeds involved, even tiny impacts generate significant heat in a small area. Maybe these micro-impacts are vaporizing nickel-rich minerals in the comet's surface, creating transient puffs of nickel vapor. It wouldn't take much, just enough tiny impacts to produce a detectable signal. Theory 3. Subsurface heating. Perhaps there's some subsurface heat source we don't fully understand. Maybe radioactive decay of long-lived isotopes deep in the comet is generating heat. Maybe tidal forces, though the sun is far away, its gravity still creates tiny stresses. Maybe something about the comet's internal structure is allowing localized heating that can vaporize metals. The truth is, as of right now, we don't have a definitive answer. The nickel detection is real. Multiple independent observations confirmed it. But the mechanism that produces it remains one of the great mysteries of 3I Atlas. Let's talk about water. Because even though 3I Atlas has less water than typical comets, the water it does have tells an interesting story. Water ice was first definitively detected in 3I Atlas's coma on July 20th, 2025 through near-infrared spectroscopic observations made by Gemini South Telescope in Chile and NASA's Infrared Telescope facility in Hawaii. The detection came from identifying the characteristic absorption features of water ice in the near-infrared part of the spectrum. By August, NASA's SphereX mission, a space telescope designed to study the cosmic infrared background, observed 3I Atlas and confirmed not only water ice, but also detected hydroxyl OH radicals. These OH radicals are actually a breakdown product of water. When water molecules, H2O, get hit by ultraviolet light from the sun, they can break apart into OH and H. The presence of OH is actually indirect evidence of water vapor being produced as the comet heats up. But here's the fascinating part. Scientists measured the water production rate and found that 3I Atlas was losing about 150 kilograms, 330 pounds, of material per second by mid-August 2025. Now, that might sound like a lot, but for a comet several kilometers across, it's actually relatively modest. Some comets in our solar system, when they get close to the sun, can lose thousands of kilograms per second. This relatively low water production, combined with the high carbon dioxide content, tells us something important about the thermal history of 3I Atlas's formation region. In its home planetary system, the region where it formed must have been cold enough that CO2 ice was more abundant than water ice, or at least the conditions favoured the retention of CO2 over H2O. Another molecule detected in 3I Atlas was hydrogen cyanide, HCN. Now, when most people hear cyanide, they think of poison. And yes, cyanide is toxic to humans. But in comets, it's actually perfectly normal. Cyanide compounds were first detected tentatively on August 22, 2025 by astronomers at Lowell Observatory, then confirmed by the Very Large Telescope on August 21st. The James Clerk Maxwell telescope in Hawaii measured the production rate of HCN and found it was producing about 1.5 times 10 to the power of 25 molecules per second in early September, rising to about 4.5 times 10 to the power of 25 molecules per second by mid-September as the comet warmed up. Why is cyanide in comets? Because comets are ancient objects that preserve the chemistry of the early solar nebula, or in this case, the nebula of whatever star system 3I Atlas came from. In the cold outer regions of protoplanetary disks, simple molecules like methane, CH4, ammonia, NH3, and water, H2O, can undergo chemical reactions driven by ultraviolet light and cosmic rays. These reactions produce more complex molecules, including hydrogen cyanide. The presence of HCN actually tells us that 3I Atlas's parent system had the right conditions for basic organic chemistry. Carbon, nitrogen, and hydrogen, three of the essential elements for life as we know it, were present and reacting together. This doesn't mean life existed there, but it does mean the basic building blocks were present. The reddish color of 3I Atlas I mentioned earlier comes from organic compounds on its surface, specifically substances called tholins, a term coined by the famous astronomer Carl Sagan to describe complex organic molecules formed by the irradiation of simpler compounds. Here's how tholins form. Take simple molecules like methane, CH4, ethane C2, H6, nitrogen, N2, and so on. Expose them to ultraviolet light or energetic particles for long periods. The radiation breaks bonds in the simple molecules and creates free radicals, highly reactive molecular fragments. These radicals recombine in various ways, creating increasingly complex organic molecules with long carbon chains and complex structures. The result is a reddish-brown tarry substance that coats the surface of objects exposed to space for long periods. Tholins are found on many objects in our outer solar system. Pluto has them, Neptune's moon Triton has them, Saturn's moon Titan has a whole atmosphere full of them. The fact that 3I Atlas has a reddish colour from tholins tells us it's been in space for a very, very long time. These compounds don't form quickly. They need millions or billions of years of radiation exposure. This ancient comet carries on its surface the accumulated effects of eons wandering through the galaxy. But here's where it gets even more interesting. Recent observations with the James Webb Space Telescope suggest that 3I Atlas has an exceptionally thick irradiated crust, much thicker than comets in our own solar system. Computer models suggest that after 1 billion years of galactic cosmic ray exposure, the surface layers of the comet would be fundamentally transformed. The ice structure would be altered, complex organic molecules would be created, and the composition would no longer resemble the pristine materials the comet was made from. In a way, 3I Atlas is wearing. Its history on its surface. It's like a ship that's been sailing for so long that its hull is covered in barnacles and weathered by storms. The comet we're seeing isn't quite the same as the one that left its home star system. It's been transformed by its journey. Let me paint a picture of what happened to 3I Atlas over the summer and fall of 2025, because this is a story of transformation. When the comet was first discovered in early July, it was about 670 million kilometers from the Sun, in the cold reaches between Mars and Jupiter. At that distance, temperatures are frigid, well below -100 degrees Celsius, -150 degrees Fahrenheit, but it was already showing signs of activity. The fact that it had a visible coma at that distance told scientists that it contained volatile ices, substances that vaporize at very low temperatures. As the comet continued its inbound journey, it was warming up. Every day, it moved roughly 5 million kilometers closer to the Sunday, and with each passing day, more sunlight hit its surface, more heat penetrated its icy exterior, and more gas began to flow. By late July, when Hubble Space Telescope captured its first detailed images on July 21st, the comet was 277 million miles from Earth. Hubble's sharp vision revealed that teardrop-shaped coma, a bright central concentration of gas and dust with a diffuse envelope extending outward. The images showed the comet was releasing dust particles at high speed, creating that classic cometary appearance. Interestingly, these early Hubble images also revealed something subtle, a faint broad tail extending in the direction toward the Sunday. This is what's called an antitail, or sunward tail, and it's actually an optical illusion caused by our viewing angle. The real tail extends away from the Sun, pushed by solar radiation pressure, but when we see the comet from certain angles, perspective makes it appear to have a tail pointing sunward. By August, multiple observatories were tracking 3I Atlas continuously. The comet was brightening steadily as it warmed up. Its apparent magnitude had increased from 17.5 at discovery to around 15 by mid-August, still too faint for most amateur telescopes, but easily visible to professional observatories and serious amateur equipment. The gas production rate was increasing as well. In early August, the Webb telescope measured a water loss rate of 150 kilograms per second. By mid-September, the hydrogen cyanide production had tripled. The comet was quite literally waking up from its billions-year-long hibernation in interstellar space. One of the most exciting moments in 3I Atlas's journey came on October 3, 2025, when the comet made its closest approach to Mars. At 4 a.m. UTC, midnight Eastern Time on October 2nd, 3I Atlas passed just 29 million kilometers from the red planet. Now, in everyday terms, 29 million kilometers is still pretty far, about 75 times the distance from Earth to the Moon. But in cosmic terms, especially for an interstellar object, this is remarkably close. The European Space Agency had been preparing for this moment for months. They had 2 spacecraft orbiting Mars, the ExoMars Trace Gas Orbiter (TGO) and Mars Express. Both spacecraft were equipped with cameras and other instruments that could observe 3I Atlas from a unique vantage point. Think about how special this was. From Earth, we see 3I Atlas from one angle, with the sun illuminating it in a particular way. But from Mars, the viewing geometry is completely different. The spacecraft could see parts of the comet that were in shadow from Earth's perspective. They could measure how the comet's brightness changed with viewing angle, which tells us about the shape and texture of the coma. They could look for jets or active regions on the nucleus that might not be visible from Earth. The ExoMars TGO captured images of 3I Atlas showing its coma and tail structure in detail, while NASA's Mars Reconnaissance Orbiter, MRO, also had the opportunity to observe the comet with its high-resolution, high-rise camera, potentially capturing the best close-up images of an interstellar object ever obtained. There's been some controversy about these MRO images. Harvard astronomer Avi Loeb publicly stated that NASA obtained images on October 2nd showing 3I Atlas when it was just 30 million kilometers from Mars, but these images were never publicly released. NASA hasn't officially commented on this, though some observers attributed delays to the US government shutdown that occurred around that time, which disrupted normal operations and data releases. Regardless, the Mars flyby provided scientists with invaluable data from a perspective we'd never get from Earth. It's like having a second pair of eyes watching from across the room. You see details and angles you'd miss from your own position. As October progressed, something inevitable happened. From Earth's perspective, 3I Atlas was moving closer and closer to the sun in the sky. Let me explain what solar conjunction means, because it's an important limitation in observational astronomy. When an object is in the same direction as the sun, as seen from Earth, we say it's in conjunction with the sunday. During this time, the object is hidden in the sun's glare and impossible to observe from ground-based telescopes. It's like trying to see a firefly next to a searchlight. The bright light overwhelms the faint object. 3I Atlas entered solar conjunction around October 22nd, 2025. For ground-based observers, the comet effectively vanished. You couldn't see it through telescopes on Earth because looking in that direction meant looking essentially toward the sun, and that's both impossible, the sun is too bright, and dangerous. Never point a telescope at the sun, unless you have proper solar filters. But here's where modern space-based astronomy becomes crucial. Just because we couldn't see 3I Atlas from Earth didn't mean we lost track of it entirely. Several spacecraft were still watching. NASA's Stereo-A spacecraft, Solar Terrestrial Relations Observatory, was designed to observe the sun and the space environment around it. From its vantage point, it could see 3I Atlas against the background stars, even when the comet was near the sun in our sky. The Solar and Heliospheric Observatory, SOHO, a joint NASA-ESA mission that's been watching the sun since 1995, has special instruments called coronagraphs that block out the sun's bright disk to study the faint corona around it. These same instruments could detect 3I Atlas as it passed behind the sunday. Even more surprising, NOAA's GOES-19 weather satellite, which primarily monitors Earth's weather and space weather, has a coronagraph instrument that can see near the sunday. Amateur comet hunter Wara Hate Boonplod was monitoring GOES-19 images and spotted 3I Atlas in the pass. Coronagraph data. These space-based observations during conjunction turned out to be absolutely crucial because they revealed something unexpected was happening to the comet. On October 29th, 2025, at approximately 14 UTC, 3I Atlas reached perihelion, its closest approach to the sunday. At this moment, the comet was 1.36 astronomical units from the sun, or about 203 million kilometers. To put that in perspective, That's farther from the Sun than Earth, which is 1 AU by definition, but closer than Mars, which orbits at about 1.5 AU. If you could somehow stand on 3I Atlas at perihelion, the Sun would appear about 30% smaller than it does from Earth, but it would still be intensely bright and hot. At this distance, the solar radiation hitting the comet would be significant. The surface temperature of the parts facing the Sun would rise dramatically, possibly to temperatures well above the freezing point of water. Though still far below room temperature, this heating would cause the most volatile ices to sublimate rapidly, creating the maximum gas production rate. For most comets in our solar system, perihelion is when they're most active, brightest, and most spectacular. It's when they develop their longest tails and brightest comas. For 3I Atlas, this moment was hidden from direct observation from Earth, but the space-based instruments watching were about to record something extraordinary. On October 28, 2025, two researchers, Carl Battams and Qicheng Zhang, were analyzing data from multiple space-based instruments: Stereo A's Secchi coronagraph, SOHO's LASCO camera, and GOES 19's CCOR1 instrument. What they found made them immediately write up and publish their findings as a rapid communication to the astronomical community. 3I Atlas had brightened dramatically, not gradually as expected, but suddenly and substantially. The comet's magnitude had jumped to approximately 9 bright, enough to be visible with binoculars if it weren't hidden behind the Sun. This brightening was far more intense than predicted based on the comet's behavior up to that point. But it wasn't just the brightness that was strange. The color had changed too. Remember how I told you 3I Atlas appeared reddish in early observations? Well, during perihelion passage, space-based observations showed it had become blue. Not just slightly blue, but distinctly bluer than the Sun, according to the technical analysis. This is weird. Really weird. Let me explain why. When sunlight scatters off dust particles, it tends to become redder. This is the same physics that makes sunsets red. Large dust grains scatter longer wavelengths preferentially, shifting the color toward red. Additionally, the tholins coating the comet's surface are known to be reddish-brown. So by all normal expectations, 3I Atlas should have become redder as it became more active and released more dust. But it became blue instead, bluer than the Sunday. There are a few possible explanations. Possibility 1. Ionized gas emission. When atoms and molecules are energized by solar radiation, they can emit light at specific wavelengths. Ionized carbon monoxide, COMAs, for instance, emits strongly in the blue and ultraviolet parts of the spectrum. If 3I Atlas was producing enormous amounts of CO and that CO was being ionized by solar radiation, the resulting glow could be blue. This would actually make sense given the comet's high CO2 content. Carbon dioxide can break down in sunlight to produce carbon monoxide, which then gets ionized. The blue color might be telling us about the unusual chemistry of this comet from another star system. Possibility 2. Unusual dust properties. Maybe the dust being released at perihelion has different properties than the dust released earlier. Perhaps heating to higher temperatures is releasing different types of dust particles, smaller ones that scatter blue light more effectively, or particles with different chemical compositions that have blue colors. Possibility 3. Something more exotic. And here's where we get into speculative territory. Some scientists, notably Avi Loeb, have suggested that the blue color could indicate something unusual, perhaps an artificially hot surface, or emissions from some kind of internal energy source. However, most planetary scientists think this is unnecessary, and that natural explanations are sufficient. The debate about what caused the blue color and rapid brightening continues. It's one of several mysteries that December 2025 observations are hoped to resolve. Alright, now we get to what might be the most controversial and debated aspect of 3I Atlas, the non-gravitational acceleration. Here's the situation. When scientists track the position of asteroids and comets, they use Newton's laws of gravity, or Einstein's general relativity, for extra precision, to predict where the object should be at any given time. If you know an object's position and velocity at one moment, and you know what gravitational forces are acting on it, you can calculate its entire future trajectory. But sometimes, comets don't follow the trajectory calculated from gravity alone. they deviate slightly from the predicted path. This is called non-gravitational acceleration, and it's been observed in many comets in our solar system. The usual explanation is the rocket effect. When a comet gets warm enough, ice is on its surface, sublimate turn from solid to gas. That gas expands rapidly and flows away from the nucleus at high speed, typically a few hundred meters per second. This outflowing gas pushes on the comet nucleus like a rocket engine, creating a small thrust. The direction of this thrust depends on where the active areas are on the nucleus and how the nucleus is rotating. If gas is primarily flowing from the sunward side, the thrust pushes the comet slightly away from the sunday. If jets are more active on one side, the comet can be pushed sideways. Over time, these tiny forces add up and cause measurable deviations from a purely gravitational orbit. For 3I Atlas, signs of non-gravitational acceleration were first reported by Davide Farnocchia, a navigation engineer at NASA's Jet Propulsion Laboratory, in late October 2025. Let me give you the technical details, then explain what they mean. The non-gravitational acceleration was detected at a distance of 1.36 AU from the Sun, at perihelion, and was characterized by two components. 1. Radial acceleration, about 135 kilometers per day squared directed away from the Sun. 2. Transverse acceleration, about 60 kilometers per day squared in the direction perpendicular to the line toward the Sun. Now, what do these numbers actually mean? Let's translate them into more intuitive terms. An acceleration of 135 kilometers day squared means that the comet's velocity was changing by 135 kilometers per day every day. Over the course of a month, this would cause the comet to deviate from its predicted position by about 10 times the diameter of Earth. A small amount by astronomical standards, but definitely measurable with precise observations. The radial component, away from the Sun, is consistent with standard cometary outgassing. Gas flowing off the sunward side would naturally push the comet away. The transverse component indicates there's some asymmetry in the outgassing. Perhaps jets are more active on one side of the nucleus than the other, or the nucleus is rotating in a way that creates a sideways push. Importantly, this level of non-gravitational acceleration is not unusual for comets. Many short-period comets in our solar system show similar or even larger accelerations. So, in principle, there's nothing extraordinary about the magnitude of the effect. Here's where the controversy begins. Avi Loeb, the Harvard astrophysicist I've mentioned several times, did a simple calculation based on the observed acceleration. Using the rocket equation and conservation of momentum, Loeb calculated how much mass the comet would need to lose to produce the observed acceleration. His conclusion: if the acceleration is due to normal cometary outgassing, 3I Atlas would need to lose at least 10-13% of its total mass over the course of about a month as it passed perihelion. Now, remember that scientists estimate 3I Atlas has a mass of at least 33 billion tons, based on the earlier observations showing it wasn't accelerating much before perihelion. Losing 10-13% of that would mean ejecting 3 to 4 billion tons of material. That's an enormous amount. When you eject billions of tons of gas and dust, it creates a massive, visible cloud around the comet. We're talking about a plume that should be obvious and dramatic in observations. Loeb's argument was essentially this: if we observe the comet in November and December 2025, we should see clear evidence of this massive mass loss. We should see a giant cloud of gas and dust. If we don't see that, then something else must be causing the acceleration, and we might need to consider alternative explanations. Let me be very clear about what Loeb is actually arguing, because this gets misrepresented a lot in media coverage. Loeb is not saying 3I Atlas is definitely an alien spacecraft. What he's saying is more nuanced. Based on the data we have, if normal cometary outgassing is causing the acceleration, we should observe specific consequences, a massive gas cloud. If we don't observe those consequences, then we should consider other possibilities, including the possibility that the acceleration might have a technological origin. His position is essentially, let's keep an open mind and let the data guide us. He's outlined several anomalies about 3I Atlas that he finds puzzling. 1. The size anomaly. It appears to be much larger than the previous two interstellar objects, which is statistically unexpected. 2. The trajectory alignment. Its orbit is aligned with the solar system's ecliptic plane to within about 5 degrees, which is uncommon for interstellar objects arriving from random directions. 3. The blue colour at perihelion, unexpected for a dusty comet. 4. The non-gravitational acceleration. Could indicate normal outgassing, or could indicate something else. 5. The rapid brightening. Faster than typical Oort cloud comets. 6. The arrival direction. Within about 9 degrees of the famous WOW signal from 1977, though this is probably coincident. 7. The nickel vapor. Detected at distances where metal shouldn't be vaporizing. 8. The perihelion timing. Passed behind the Sun from Earth's view, creating a blind spot. 9. The lack of a large visible debris cloud, if confirmed in December observations. Loeb's argument is that individually each anomaly might have a natural explanation, but taken together, they make 3I Atlas unusual enough that we should carefully examine all possibilities. On the other side of this debate is the vast majority of planetary scientists who specialise in comets. Professor Megan Schwamm from Queen's University Belfast summarised the mainstream view. The analysis of efforts from many astronomers around the globe show that, to the best of our knowledge, 3I Atlas is consistent with having a natural origin. Its properties to date are consistent with it being an icy planetesimal that formed around another star in the galaxy. Here's the conventional explanation for each of the so-called anomalies. The size? Yes, 3I Atlas is large, but that might just mean we got lucky and detected a big one. The population of interstellar objects almost certainly spans a wide range of sizes, and larger objects are easier to detect, even though they're rarer. The trajectory alignment. While the close alignment with the ecliptic might seem improbable, you have to remember that 3I Atlas likely came from the thick disk of the Milky Way, where the distribution of velocities isn't completely random. Objects from that population might naturally arrive at angles that are somewhat aligned with the galactic plane. The blue colour, most likely due to strong emission from ionized carbon monoxide or other molecules, combined with the unusual viewing geometry during perihelion. Comets with unusual chemistry can display unusual colours. The non-gravitational acceleration, standard cometary outgassing. The outgassing doesn't need to be visible as a massive cloud from our viewing angle, especially if the gas is transparent or if the dust-to-gas ratio is lower than typical comets. The rapid brightening could be due to the comet's unusual composition, high CO2 content, causing more vigorous sublimation than expected. Or it could be a small outburst, a sudden release of material which is common in comets. The nickel vapor. While unusual, it's explainable through the irradiated crust, model or through micrometeorite impacts, vaporizing metal-rich minerals. The perihelion timing. Pure coincidence. The comet's orbit was determined by its trajectory through the galaxy, not by any desire to hide from Earth's view. The debris cloud. We won't know until December observations, but the expectation is that gas and dust are being released, even if they're not as obvious as some predictions suggested. In short, the mainstream view is that 3I Atlas is genuinely unusual and scientifically fascinating, but it's unusual in ways that are explainable by natural processes. It's a comet from another star system with somewhat different chemistry and history than comets in our own system, but it's still fundamentally a comet. As of early November 2025, 3I Atlas is on its way back out from the Sunday. It emerged from behind the Sun's glare and became visible again to ground-based telescopes in mid-November. The crucial observations will come in December 2025, particularly around December 19th, when the comet makes its closest approach to Earth at 270 million kilometers distance. Multiple observatories have scheduled time to observe 3I Atlas. The Hubble Space Telescope will perform ultraviolet spectroscopy to measure gas production rates and characterize the coma. The James Webb Space Telescope will conduct follow-up near-infrared observations to measure composition and activity levels. The International Asteroid Warning Network has organized a coordinated observing campaign involving dozens of telescopes worldwide. What are they looking for? Evidence of significant mass loss. If 3I Atlas is losing billions of tons of material due to cometary outgassing, it should be obvious. The coma should be large and bright. spectroscopic observations should detect strong gas emission lines. The dust production should be substantial. If those features are observed, it confirms that standard cometary processes explain the non-gravitational acceleration, and the debate is essentially settled. 3I Atlas is a natural, if unusual, comet. If, however, observations fail to detect the expected level of mass loss, then things get more interesting. It would mean scientists need to find another explanation for the acceleration. That doesn't automatically mean alien spacecraft, but it would mean our understanding of how comets behave is incomplete. The story will be that 3I Atlas is a genuinely interesting natural object with some unusual properties due to its composition and history, but it's not evidence of extraterrestrial technology. Science is about following the data, and in a few weeks, we'll have the data. Let me take a step back now and compare all three known interstellar visitors, because each one teaches us something different. Oumuamua, discovered in October 2017, remains the most mysterious. It was roughly 400 meters long and had that extremely elongated shape, about 10:1 length to width ratio. It tumbled through space with a 7.3-hour rotation period, causing its brightness to vary by a factor of 10 as different faces came in and out of view. The big mystery was its composition. It showed no visible coma, no tail, no detectable outgassing, yet it accelerated away from the sun faster than gravity alone could explain. Various scientists proposed it was made of nitrogen ice, like Pluto's surface, hydrogen ice, frozen H2 formed in cold interstellar clouds, or had a water ice interior covered by an insulating crust. Avi Loeb's controversial paper suggesting Oumuamua might be a light sail, an artificially thin object propelled by radiation pressure, sparked enormous public interest and debate. Most scientists remained skeptical, pointing to the 2023 research showing that outgassing of molecular hydrogen could explain the acceleration without requiring exotic explanations. But the key point is, Oumuamua didn't fit neatly into any category. It was asteroid-like in appearance but comet-like in motion. It was neither fish nor fowl. 2I Borisov, discovered in August 2019, was in many ways the opposite of Oumuamua. From day one, it looked like a comet. It had a bright coma, a visible tail, and spectroscopic observations detected the classic cometary molecules: cyanide, Cn, carbon monoxide, CO, water, H2O. Its nucleus was estimated to be about 1 kilometer across, and it was releasing dust and gas at rates similar to comets in our solar system. Its color was similar to solar system comets. It even underwent a small fragmentation event in March 2020 when a chunk broke off the nucleus, something that happens to solar system comets occasionally. In terms of composition, detailed studies showed 2I Borisov was rich in CO relative to water, more so than typical solar system comets, but not extraordinarily so. Its dust had unusual polarimetric properties, suggesting the dust grains were similar to those in comet Hale-Bopp, another pristine comet that probably never passed close to the sun before 1997. Scientists concluded that 2I Borisov was remarkably similar to the most pristine comets in our outer solar system, particularly those in the Oort cloud that haven't been heavily processed by repeated passages near the Sunday. The take-home message from 2I Borisov was comforting. Comets from other star systems can look a lot like comets from our own system. The basic physics and chemistry of comet formation seems to be universal. Now we have 3I Atlas, and it's interesting because it's sort of a hybrid between the previous two. Like Oumuamua, it's large, probably several kilometers across, based on the best current estimates. Like Oumuamua, it shows non-gravitational acceleration and some features that don't quite match typical solar system comets. But like 2I Borisov, it clearly shows cometary activity. It has a coma, a tail, and spectroscopic detections of multiple gases. It looks and behaves like a comet, even if some of its properties are unusual. If I had to characterize the three, Oumuamua, mysterious, asteroid-like, possibly exotic composition; 2I Borisov, familiar, comet-like, reassuringly normal; 3I Atlas, comet-like but with unusual chemistry and behavior; The pattern that emerges is that interstellar objects are diverse. They don't all look the same. They come from different stellar systems with different formation conditions. Some are pristine, never heated ice balls. Some might be fragments of larger bodies. Some might be heavily processed by radiation. Some might be rich in one type of ice, others in different ices. This diversity is actually what we should expect. Our own solar system has enormous diversity in its small bodies, from metallic asteroids to icy comets, to strange objects like centaurs that blur the line between the two. Why should other stellar systems be any less diverse? The chemistry of 3I Atlas, particularly its high CO2 content, tells us something profound about its home system. In our solar system, objects rich in CO2 formed far from the Sun, beyond the CO2 ice line. This suggests that 3I Atlas's parent system had a similar temperature structure, warm close to the star, cold farther out, with different ices condensing at different distances. But the exact ratio of different ices depends on the chemistry of the protoplanetary disk, which in turn depends on the composition of the molecular cloud from which the star formed. Stars in different parts of the galaxy formed from clouds with different chemical compositions. Older stars formed from gas that had fewer heavy elements, astronomers call. Elements heavier than hydrogen and helium. Metals, even though that includes things like carbon and oxygen. Younger stars formed from gas enriched by previous generations of stars that created heavy elements through nuclear fusion and scattered them via supernovae. The fact that 3I Atlas came from the thick disk of the Milky Way, a population of old stars, means it might have formed around a star with lower metallicity than our Sunday. This could affect the relative abundances of different ices in its protoplanetary disk. Additionally, the architecture of a planetary system affects what gets ejected. If 3I Atlas's home system had giant planets at certain orbital distances, those giants would preferentially scatter objects from specific zones. The composition of 3I Atlas might tell us where in its home system it formed, which in turn constrains what that system might have looked like. In other words, every interstellar visitor is a messenger carrying information about its parent system. By studying enough of these objects, which we'll be able to do once the Vera Rubin Observatory is fully operational, we can build up a statistical understanding of planet formation throughout the galaxy. Let me take you on a journey through time and space to understand how planetary systems, including the one that produced 3I Atlas, actually form, because this is one of the grandest stories in all of science. It begins with a molecular cloud, a vast region of space, light years across, filled with gas and dust at extremely low density and temperature. Most of the mass is hydrogen and helium left over from the Big Bang, but there's also a smattering of heavier elements: oxygen, carbon, nitrogen, silicon, iron, and so on. These heavier elements were created inside previous generations of stars and scattered through space when those stars died. Something disturbs this cloud. Maybe a nearby supernova sends a shockwave through it. Maybe the cloud passes through a galactic spiral arm where compression occurs. Whatever the cause, part of the cloud begins to collapse under its own gravity. As it collapses, it spins faster and faster, like an ice skater pulling in their arms. The cloud flattens into a disk, a protoplanetary disk, with a growing star forming at the center. This is how our Sun formed 4.6 billion years ago. This is how 3I Atlas's parent star formed, probably 8 to 10 billion years ago or more. Within this disk, magic happens. Let me slow down and explain the process step by step, because it's mind-blowingly complex and beautiful. Initially, the disk is filled with tiny dust grains, particles smaller than smoke particles, maybe a micrometer, 1/1,000,000th of a meter across. These grains are made of various materials: silicates, rocky minerals, carbonaceous material, water ice if it's cold enough, and frozen gases. How do micron-sized dust grains grow into kilometer-sized planetesimals? This is actually one of the hardest problems in planet formation theory. The grains are zipping around in the disk at different speeds, colliding frequently. When they collide gently, van der Waals forces, weak attractive forces between molecules, can make them stick together, growing larger. But there's a problem called the meter-size barrier. Once particles grow to about centimeter or meter size, they start feeling significant drag from the gas in the disk. This drag causes them to lose angular momentum and spiral inward toward the star extremely rapidly, on timescales of just 100 to 1,000 years. They should fall into the star before they can grow larger. So how do we get past this barrier? Scientists have proposed several mechanisms. Mechanism 1. Streaming instabilities. In regions where the dust-to-gas ratio is high enough, the dust can collectively create its own gravity and clump together directly into larger bodies, skipping the problematic meter-sized stage entirely. Mechanism 2. Pebble accretion. Slightly larger bodies, maybe boulder-sized, can gravitationally focus the flow of smaller pebbles toward them, growing rapidly. Computer simulations show this can be incredibly efficient. Mechanism 3. Pressure bumps. In regions where the gas pressure has local maxima, dust particles can collect and concentrate, making collisions and growth more likely. The truth is probably a combination of these mechanisms acting together, but somehow, the disk manages to produce planetesimals, objects tens to hundreds of kilometers across. Once you have planetesimals, gravity takes over. These kilometer-sized bodies gravitationally attract each other. They collide, merge, and grow larger. The larger they get, the stronger their gravity, and the more efficiently they can attract more material. It's a runaway process. Over timescales of millions of years, planetesimals grow into planetary embryos, bodies ranging from moon-sized to Mars-sized, roughly 1,000 to 5,000 kilometers across. In the inner solar system, where temperatures are warm and only rocky materials can condense, these embryos are made of rock and metal. In the outer solar system, where it's cold enough for water ice to freeze, embryos can incorporate ice and become much more massive more quickly. Here's where it gets really interesting. In the cold outer regions of the disk, beyond the snow line or ice line, the distance where water ice is stable, planetary embryos can grow very large. Ice is abundant. There's much more oxygen in the form of water ice than there is silicon in the form of rocks. So in the icy regions, cores can grow to 5 to 15 Earth masses relatively quickly. Once a core reaches about 10 Earth masses, something dramatic happens. Its gravity becomes strong enough to start capturing gas from the surrounding disk. At first, this happens slowly. The gas forms a slowly growing envelope around the solid core. But once the envelope mass becomes comparable to the core mass, runaway gas accretion begins. In just 10,000 to 100,000 years, a blink of an eye in cosmic terms, the planet can swell to Jupiter-like proportions, accumulating hundreds of Earth masses of hydrogen and helium. This is how gas giants form in the core accretion model, the most widely accepted theory of giant planet formation. There's an alternative called disk instability, where parts of the gas disk can directly collapse under their own gravity to form giant planets without needing a solid core first. But most scientists think core accretion is the dominant mechanism, at least in our solar system. Now, here's the part that's crucial for understanding objects like 3I Atlas. Planets don't stay where they form. When a planet grows in a gas disk, it creates disturbances in that disk. The planet's gravity creates spiral density waves, ripples in the gas that propagate outward and inward from the planet's orbit. These waves carry angular momentum, and, through their interaction with the planet, they can transfer angular momentum to or from the planet. If the net effect is to remove angular momentum from the planet spirals inward toward the star. If angular momentum is added, it spirals outward. The direction and rate of migration depend on complex factors: the planet's mass, the disk's properties, density, temperature, viscosity, and the precise location in the disk. For planets smaller than about Saturn's mass, the usual situation is inward migration, and it can be fast, terrifyingly fast. A Neptune-mass planet could migrate from Jupiter's orbit to Mercury's orbit in just 100,000 years if conditions are right. This is called Type 1 migration. Larger planets, once they get massive enough, can actually open a gap in the gas disk. They gravitationally clear out a ring around their orbit. These planets migrate more slowly, at the rate the disk itself is evolving, in what's called Type 2 migration. But they still migrate. This migration has profound consequences. As giant planets move through the disk, they gravitationally scatter smaller objects. Some planetesimals are thrown into the star, some are kicked into highly elliptical orbits, and some, like 3I Atlas, are accelerated to such high velocities that they escape the stellar system entirely, becoming interstellar wanderers. Let me tell you about what probably happened in our own solar system, because it illustrates how chaotic and violent planet formation can be. According to the Nice model, named after the French city, pronounced Nice, the giant planets in our solar system didn't form in their current locations. Jupiter probably formed around 3.5 AU, astronomical units, from the Sun, Saturn at about 6 AU, and Neptune and Uranus even farther out, maybe 15 to 20 AU. Initially, the giant planets were in a compact configuration, probably locked in orbital resonances with each other. For about 500 to 600 million years, this configuration remained relatively stable, but it was sitting on a powder keg. Then something happened. Possibly, Jupiter and Saturn crossed a 2-to-1 resonance, where Saturn orbited once for every 2 Jupiter orbits. This resonance crossing destabilized the entire system. The giant planets' orbits became eccentric. They began scattering each other gravitationally. Jupiter, being the most massive, mostly stayed put but moved slightly inward. Saturn was kicked outward. Neptune surged past Uranus and ploughed into the primordial Kuiper belt, a massive disk of icy planetesimals extending from about 30 to 50 AU. The result was cataclysmic. Neptune and the other giants scattered these planetesimals by the billions. Some were thrown into the inner solar system, causing the late heavy bombardment, a period about 3.9 billion years ago when the Moon, Earth, Mars, and other inner solar system bodies were pummeled by impacts. You can still see the craters this bombardment created on the Moon's surface. Some planetesimals were captured into stable resonances with Neptune, creating populations like the Plutinos, objects in 3 to 2 resonance with Neptune, like Pluto. Some were kicked into the Oort cloud, a vast spherical cloud of comets extending up to 100,000 AU from the Sun, nearly halfway to the nearest star, and some, perhaps millions of them, were accelerated to such high velocities that they escaped the solar system entirely. These objects are now wandering through interstellar space, perhaps occasionally passing through other star systems. Some of them might be getting detected by alien astronomers around distant stars, just as we're detecting 3I Atlas from some other system. Here's something fascinating. When we look at exoplanets, planets around other stars, we find that our solar system is actually kind of unusual. Many exoplanetary systems have hot Jupiters, Jupiter-mass planets orbiting their stars in just a few days, far closer than Mercury orbits our Sunday. These planets couldn't have formed where they are. It's too hot for hydrogen to condense, and there's not enough mass in such a small region. They must have formed farther out and migrated inward. But our Jupiter didn't do that. Why not? Scientists think Jupiter started migrating inward, but was halted and even reversed. Saturn, forming slightly later and farther out, caught up with Jupiter. When they locked into a 2 to 3 resonance, their mutual gravitational influence became strong enough to reverse their migration. This is called the grand tack hypothesis. Jupiter tacked like a sailboat, reversing direction. This reversal might have been crucial for Earth's existence. If Jupiter had continued migrating inward, it might have disrupted the formation of terrestrial planets or even sent them crashing into the Sunday. Jupiter's outward migration instead cleared out material from the inner solar system, setting the stage for small rocky planets like Earth to form. In other star systems without Jupiter's fortuitous reversal, giant planets might have migrated all the way in, creating hot Jupiter systems with no terrestrial planets at all. Or the giants might have scattered all the material out of the system, leaving nothing behind. This helps explain why exoplanetary systems show such enormous diversity. Every system's history is different, depending on when planets formed, how massive they got, what resonances they encountered, and when the gas disk dissipated. So where does 3I Atlas fit into this story? Somewhere in the Milky Way galaxy, probably 8 to 10 billion years ago, based on its trajectory suggesting it came from the old stellar population of the thick disk. A star was born. A protoplanetary disk formed around that star. Within that disk, dust grains began sticking together, planetesimals formed, and eventually planets grew. In the cold outer reaches of that disk, beyond the CO2 ice line, a comet formed. This comet, the object that would eventually become 3I Atlas, was probably similar to billions of other comets in that system. It was a few kilometers across, made of Isis.2, H.2, OCO, and other volatiles, mixed with rocky and carbonaceous material. For millions of years, this comet orbited its parent star in the outer regions, gradually accumulating a surface crust of organic compounds as cosmic rays and ultraviolet light processed its surface materials. Then something changed. Perhaps a giant planet in that system underwent migration, stirring up the region where comets resided. Perhaps the comet had a close encounter with a planet or another large body. Perhaps gravitational perturbations from a passing star disrupted the outer regions of the system. Whatever the cause, 3I Atlas was accelerated to high velocity, high enough to exceed its star's escape velocity. It was ejected from the system, and then it wandered. For billions of years, 3I Atlas drifted through the galaxy, one lonely ice ball among countless trillions. It passed through vast clouds of interstellar gas. It was bombarded by cosmic rays. It slowly tumbled through the void, far from any star, at temperatures just a few degrees above absolute zero, until, by pure chance, its path intersected with another stellar system, ours. The sun's gravity bent its trajectory, temporarily capturing it into a hyperbolic flyby. For a brief few months in 2025, this ancient wanderer passes through our solar system, offering us a glimpse into its distant origin before it returns to the darkness. As of early November 2025, 3I Atlas has emerged from behind the sun and is once again visible from Earth. But it's changed. Having passed perihelion on October 29th, the comet has been heated to its maximum temperature and should be at or near its peak activity level. Ground-based observers, with telescopes of at least 8 inches, 20 centimeters in diameter, can now spot it in the pre-dawn sky, moving through the constellation Virgo. The comet's brightness is estimated to be around magnitude 11.5 inches early November, fading slowly as it moves away from both the Sun and Earth. While that's too faint for the naked eye or binoculars, it's easily within reach of amateur astronomers with moderate equipment and dark skies. What makes November particularly exciting is that this is the first chance for ground-based observers to see 3I Atlas after its perihelion passage. The space-based observations during conjunction told us the comet brightened dramatically and turned blue, but now we can see it directly from Earth with the full arsenal of ground-based telescopes. Observatories around the world are tracking it nightly. The Virtual Telescope project in Italy is offering online viewing sessions where people worldwide can watch 3I Atlas in real time. Professional astronomers are collecting photometric data, brightness measurements, spectroscopic data, composition measurements, and imaging to track any changes in the coma structure or tail development. Mark your calendar, December 19th, 2025. That's when 3I Atlas makes its closest approach to Earth, passing at a distance of 1.8 astronomical units, about 270 million kilometers, or 167 million miles. This is still far, about 700 times the distance from Earth to the Moon, but in astronomical terms, it's quite close. More importantly, it's the optimal time for detailed observations, because the comet will be well placed in the sky, away from the sun's glare, and at its minimum distance from our planet and our telescopes. The International Asteroid Warning Network has coordinated an observing campaign running from late November through late January. This campaign involves dozens of telescopes worldwide, from small amateur instruments to major professional observatories. The goal is to collect as much data as possible while the comet is favourably positioned. What are they looking for specifically? 1. Gas production rates. By measuring the strength of emission lines from molecules like H2O, CO2, CO, HCN, and others, scientists can determine how much gas the comet is producing. This directly addresses the mass loss question. If the comet lost 10-13% of its mass at perihelion, The gas production should be substantial and measurable. 2. Coma structure. High-resolution imaging can reveal jets, shells, and other structures in the coma. These features tell us about active regions on the nucleus and how gas and dust are being released. If there's massive outgassing, it should be obvious in the coma morphology. 3. Dust properties. By analysing scattered sunlight at different wavelengths and polarizations, scientists can determine the size, distribution, and composition of dust particles. This helps understand what's happening on the comet's surface. 4. Nuclear size. While the nucleus itself is too small to resolve, directly it's only a few kilometers across, at a distance of 270 million kilometers. Careful analysis of the brightness and coma can constrain the nucleus size more precisely than current estimates. 5. Rotation period. If the nucleus is irregular in shape, its brightness should vary periodically as it rotates. Measuring this rotation period tells us about the nucleus's shape and potentially about internal structure. The Hubble Space Telescope is scheduled to observe 3I Atlas in November and continuing through December. Hubble will use its Space Telescope Imaging Spectrograph, STIS, to obtain ultraviolet spectra of the comet. Why is UV spectroscopy important? Many molecules that are hard to detect at visible wavelengths have strong signatures in the ultraviolet. Hydroxyl, OH, atomic oxygen, carbon, and sulfur all have prominent UV spectral features. By measuring these, scientists can determine elemental abundance ratios like sulfur to oxygen, which is a diagnostic of formation conditions. UV observations also help detect very faint gas emission that might be invisible at other wavelengths. If 3I Atlas is producing significant amounts of gas that's somehow transparent or invisible at visible wavelengths, the UV data should reveal it. Hubble will also take high-resolution images in multiple filters. These images will show the coma structure in exquisite detail, potentially revealing features that ground-based telescopes miss due to atmospheric blurring. The James Webb Space Telescope will conduct follow-up observations in December 2025. Webb observed 3I Atlas once in August, but that was before perihelion. The December observations will show how the comet changed after its close pass. By the Sunday Webb's near-infrared spectrograph, NIRSpec, can detect molecules that have spectral features in the infrared. This includes CO2, COH2O, CH4, and many organic molecules. By comparing the August pre-perihelion spectrum with the December post-perihelion spectrum, scientists can see how the comet's composition and activity changed. Importantly, Webb can also detect very cold emissions from distant parts of the coma. If there's a massive debris cloud surrounding the nucleus, the kind that should exist if billions of tons of material were ejected at perihelion, Webb should see it. While space telescopes get a lot of attention, ground-based observatories play a crucial role too. They can observe for longer periods, space telescopes have limited time available, can obtain data across a wider range of wavelengths, and there are simply more of them. Major professional observatories participating in the 3I Atlas campaign include the Very Large Telescope, VLT in Chile, 4 8.2-meter telescopes that can work together, the Gemini telescopes in Hawaii and Chile, each 8.1 meters in diameter, the Subaru telescope in Hawaii, 8.2 meters with specialized instruments, the Keck Observatory in Hawaii, 2 10-meter telescopes, the Large Binocular Telescope in Arizona, effectively 11.8 meters of collecting area. These large telescopes can obtain spectroscopy of the comet, showing detailed chemical composition. They can take time series images showing how the coma changes hour by hour. They can measure polarization, which reveals properties of the dust grains. But even smaller telescopes contribute valuable data. Amateur astronomers with 8 to 16-inch telescopes can measure the comet's brightness and track how it changes over time. Networks of small robotic telescopes can monitor the comet continuously, catching transient events like outbursts or sudden changes. The distributed, multi-wavelength, multi-instrument approach is how modern astronomy tackles complex objects. No single telescope can do everything, but together, the global community of observers can build up a complete picture. Let me paint two scenarios for what the December observations might reveal. Scenario 1. Confirmation of natural processes. In this scenario, the observations show clear evidence of robust outgassing. The spectroscopy reveals strong emission lines from water vapor, carbon dioxide, carbon monoxide, and other molecules. The measured gas production rates are high enough to account for the non-gravitational acceleration observed at perihelion. The coma shows structure consistent with active jets from specific regions on the nucleus. Dust is being produced at rates consistent with cometry models. The UV observations detect the expected molecules. Everything fits together into a coherent picture. 3I Atlas is a comet with unusual but explainable chemistry, probably due to its formation in a different stellar system with different conditions than our solar system. The scientific papers will conclude that while 3I Atlas is interesting and teaches us about interstellar chemistry and planet formation diversity, it is fundamentally a natural object. A comet formed billions of years ago in another star system, ejected into interstellar space, and now passing through our solar system on its way back to the galaxy. This is the scenario most planetary scientists expect. Scenario 2. An unexpected result. In this alternative scenario, the observations fail to detect the level of gas and dust production expected based on the perihelion acceleration. The coma is present but modest. Spectroscopy shows gas production, but not at the levels needed to explain the acceleration. The dust-to-gas ratio is unusual. The structure of the coma doesn't show the massive debris cloud that should exist if billions of tons were ejected. In this case, scientists would need to reconsider. Perhaps the composition is so unusual that standard cometry models don't apply. Perhaps there's some heat source or mechanism we don't understand causing the acceleration. Perhaps the mass of the comet is different than estimated. Perhaps outgassing occurred in a way we didn't predict. Maybe highly collimated jets that were missed in observations, or transparent gas that's hard to detect. This wouldn't immediately prove the object is artificial, but it would mean our understanding is incomplete. It would spark intensive modelling efforts to find natural explanations that fit the data. And yes, it would mean that more exotic possibilities, including the remote chance of technological origin, would need to be taken more seriously. I want to emphasize, even in scenario 2, the most likely explanation would still be natural processes we haven't fully understood yet, not alien technology. But it would be scientifically exciting because it would mean we're learning something new about how comets work. Let's zoom out and talk about why 3I Atlas and other interstellar objects matter beyond just the immediate excitement of discovery. Every interstellar object is a sample from another planetary system. Think about what that means. We've spent decades building increasingly powerful telescopes to study exoplanets, planets orbiting other stars. We can detect these planets, measure their sizes and masses, sometimes even analyze their atmospheres with spectroscopy. But there's a fundamental limit. These planets are light years away. We can't send spacecraft to them with current technology. We can't collect samples. We can observe them remotely, but we're always limited by distance and the fact that they're incredibly faint compared to their parent stars. Interstellar objects like 3I Atlas are different. They come to us. They're in our solar system, close enough to study in detail with our best instruments. They're samples of material from other stellar systems that we can analyze without having to travel light years to collect them. The composition of 3I Atlas tells us about the chemistry of its home protoplanetary disk. The ratio of different ices, CO2 versus H2, O versus CO, tells us about temperature, gradients in that disk. The presence of certain molecules tells us what elements were available. The properties of the dust tell us about the solid materials that were present. All of this feeds into our understanding of planet formation as a universal process. Are the conditions in other planetary systems similar to ours, or radically different? Do planets form through the same mechanisms everywhere, or are there alternative pathways we haven't considered? Are the building blocks of planets, volatiles like water, and organics like carbon compounds common throughout the galaxy, or rare and precious? These aren't just abstract questions. They affect our understanding of where life could arise in the universe. Here's something profound that connects interstellar objects to the origin of life. Planetary systems constantly exchange material. Think about it. Every star system ejects millions of planetesimals during planet formation. These objects scatter through the galaxy. Occasionally, they pass through other star systems. Sometimes they're captured, becoming new members of that system. Sometimes they impact planets in the system. This means that material is constantly being redistributed throughout the galaxy. Water, organic compounds, even complex molecules formed in one stellar system can be transported to another system. Now consider Earth's early history. When Earth formed 4.5 billion years ago, it was hot, really hot. Molten rock surface, frequent impacts from planetesimals, intense heat from gravitational contraction, and radioactive decay. Under these conditions, any water or volatile compounds would have been lost, boiled away into space. Yet today, Earth has oceans. About 70% of the surface is covered with water. Where did all that water come from? The leading theory is that it was delivered by impacts from water-rich objects, comets and asteroids from the outer solar system that crashed into Earth after it cooled down enough for water to be retained. These impacts brought water, and they also brought organic compounds, amino acids, simple sugars, nucleobases, the building blocks of DNA and RNA, and other molecules important for life. But here's the question. Could some of Earth's water and organics have come from interstellar sources? If our solar system is constantly being visited by interstellar objects, and we now know it is, remember, there are probably 10,000 of them inside Neptune's orbit right now, and if some of these objects occasionally impact planets, then Earth has likely been hit by interstellar comets and asteroids many times over its 4.5 billion year history. Most of these impacts would have occurred early in Earth's history when bombardment rates were higher. An interstellar comet crashing into the young Earth would have delivered whatever volatiles and organics it carried from its home system. This means Earth's water and the building blocks for life might include contributions from other star systems. We might literally be made, in part, from material that came from another stellar system. And if that's true for Earth, it's true for every planet in every system throughout the galaxy. There's a constant low-level exchange of material between stellar systems. The galaxy is interconnected in a way most people don't realize. This has implications for the origin of life itself. If the building blocks for life are distributed widely through the galaxy, delivered by impacts from wandering objects, then life might be more common than we thought. Or conversely, if life is rare, these interstellar wanderers might be one mechanism by which life could spread from one system to another, a process called panspermia. Right now, we're in the early days of interstellar object astronomy. 3 confirmed objects in 8 years isn't much to build statistical inferences from, but that's about to change dramatically. The Vera C. Rubin Observatory, which became operational in 2025, is a game changer. Its 8.4 meter mirror and 3.2 gigapixel camera can photograph the entire visible sky every few nights. Its automated data pipeline will detect anything that moves, changes, or appears. Scientists predict Rubin will discover dozens to potentially hundreds of interstellar objects per year once it's fully operational. Within a decade, we could have a catalogue of hundreds of these visitors. With that kind of sample size, we can start doing real statistics. We can ask questions like, what is the size distribution of interstellar objects? Are most of them small, or is there a broad range? What fraction are comets versus asteroids? What compositional types exist? Are CO2, rich comets like 3I, Atlas common or rare? Do objects from different galactic populations, young stars versus old stars, have different properties? Are there correlations between composition and velocity, between size and activity? How common are truly weird objects, like Oumuamua? These statistical answers will transform our understanding of planet formation throughout the galaxy. They'll tell us whether our solar system is typical or unusual. They'll reveal the diversity of planetary systems and constrain the physics of planet formation and ejection. And here's the really exciting part. With hundreds of detected objects, if there is anything artificial out there, if even 0.1% of interstellar objects are technological rather than natural, we'd detect it in the statistics. Objects with genuinely anomalous properties that don't fit natural explanations would stand out clearly when compared to hundreds of normal objects. So, in a sense, The next decade will settle questions that we can only speculate about now. The sample size will become large enough for robust conclusions. There's a dream that many planetary scientists share, sending a spacecraft to rendezvous with an interstellar object and study it up close. The European Space Agency has already approved a mission concept called Comet Interceptor, scheduled for launch in 2029. This mission has a clever design. Rather than launching toward a specific target, it will wait in space at the L2 Lagrange point, a gravitationally stable location, about 1.5 million kilometers from Earth. When a promising target is discovered, ideally a pristine comet or an interstellar object, the spacecraft will spring into action, using its propulsion system to intercept the target. The advantage of this approach is flexibility. With traditional missions, you choose your target and design your trajectory years in advance. If a rare object like an interstellar visitor appears, you can't react fast enough. But with Comet Interceptor waiting in space, it could potentially reach a newly discovered interstellar object within months of detection. Imagine what a close-up mission to an interstellar object could accomplish. High-resolution imaging showing the nucleus surface in detail, craters, layering, color variations, active regions, in situ composition measurements analyzing gas and dust directly, without having to view through Earth's atmosphere. Surface composition using spectrometers that can identify specific minerals and ices. Magnetic field measurements revealing whether the object has any magnetism. Some asteroids do, comets typically don't. Internal structure using radar or seismic measurements to see inside the object. Sample collection, potentially even gathering physical samples to return to Earth or analyze on the spacecraft. Such a step. Mission would answer definitively many questions that spectroscopy from Earth can only address indirectly. Of course, there are enormous challenges. Interstellar objects are fast, typically 20-40 kilometers per second relative to the Sunday matching velocities requires huge amounts of propulsion. Even with gravitational assists from planets, it's difficult and fuel intensive. For 3I Atlas specifically, the opportunity has passed. By the time such a mission could be organized and launched, 3I Atlas will be far beyond reach. But for future visitors detected early enough, particularly with Rubin's improved discovery rate, a rendezvous mission might be possible. Finally, let me connect this to perhaps the deepest question in all of science. Are we alone in the universe? The discovery of interstellar objects doesn't directly answer this question, of course, but it provides context and informs how we think about it. First, the mere existence of interstellar objects, and their apparent abundance, means that the exchange of material between stellar systems is an ongoing process. If life arose in one system, its chemical signatures, organic molecules, biological patterns, could potentially be carried to other systems by these wanderers. Second, studying the diversity of planetary systems through their ejected debris tells us about the range of environments where planets form. Are water and organic molecules common? Do all systems produce similar types of objects, or is there wide variation? The answers affect our estimates of how many potentially habitable planets exist in the galaxy. Third, and most speculatively, if technological civilizations exist elsewhere, they might use interstellar objects as resources, or even as transportation. A sufficiently advanced civilization could potentially detect approaching interstellar objects, intercept them, and either mine them for materials or use them as free rides through the galaxy, since they're already moving at interstellar velocities. This is pure speculation, of course, and most scientists think it's unlikely, but it's not physically impossible, and the debate around Oumuamua and now 3I Atlas has brought these ideas into mainstream scientific discussion in a way they weren't before. The key point is this: we live in a galaxy where material constantly moves between stellar systems. We're not isolated. Our solar system has been visited by countless interstellar objects throughout its history, and will be visited by countless more in its future. Understanding these visitors helps us understand our place in the cosmic ecosystem. So here we are, in early November 2025, watching 3I Atlas recede from the sun and head back toward the darkness between stars. We've learned an enormous amount about this cosmic wanderer. We know it's several kilometers across, probably weighing at least 33 billion tons. We know it's remarkably rich in carbon dioxide, suggesting it formed far from its parent star. We know it's been transformed by billions of years of cosmic ray bombardment. We know it contains nickel that somehow vaporizes at impossibly cold temperatures. We know it brightened dramatically and turned blue as it passed behind the Sunday. We know it experienced non-gravitational acceleration near perihelion. But there's still so much we don't know. The critical observations in December will help answer remaining questions. Will we see evidence of the massive gas and dust cloud that should exist if billions of tons of material were ejected? Will the composition measurements confirm our theories about its formation environment? Will its behavior after perihelion match predictions? Or will it surprise us yet again? The beauty of science is that we don't have to speculate. We can observe, measure, and test our hypotheses. In just a few weeks, we'll have the data. What has 3I Atlas taught us so far? Regardless of what the December observations show, interstellar objects are diverse from the weird, elongated Oumuamua to the familiar-looking 2I, Borisov to the chemically unusual 3I Atlas. We've learned that interstellar visitors come in many varieties. There's no single typical interstellar object. They reflect the diversity of conditions in the planetary systems where they formed and the varied histories of their billion-year journeys through space. Our technology is ready. We are now capable of detecting and studying these visitors in detail. The global network of survey telescopes, space-based observatories like Hubble and Webb, and the coordination between professional and amateur astronomers. All of this infrastructure allows us to respond rapidly to discoveries and gather comprehensive data. We're no longer caught off guard by these objects. We're ready for them. Science works by debate and data. The controversy around 3I Atlas, with scientists like Avi Loeb proposing unconventional interpretations, while most of the community favors natural explanations, shows how science is supposed to work. Ideas are proposed, debated, and tested against evidence. It's not a process of authority or consensus, but of data. The universe doesn't care about our opinions. It will reveal its truths through observations. We're part of a galactic ecosystem. Perhaps most profound, 3I Atlas reminds us that our solar system isn't isolated. Material flows through the galaxy, visiting stellar system after stellar system. We're connected to the rest of the galaxy through these wandering messengers. Some of the atoms in our bodies might have come from another star system, delivered by impacts billions of years ago. It's humbling and awe-inspiring. Even as 3I Atlas leaves, the story of interstellar object exploration is just beginning. The Vera Rubin Observatory will transform this field from the study of rare, special events into a systematic science. Within the next decade, we'll detect enough interstellar visitors to build up statistical catalogues. We'll start to see patterns and trends. We'll be able to distinguish between common object types and truly unusual outliers. NASA and ESA are both developing plans for dedicated interstellar object interceptor missions. The technology exists. We just need the funding and political will to make it happen. Imagine spacecraft sitting ready, in Earth orbit or at Lagrange points, waiting for the next interesting visitor to be discovered, ready to launch within weeks to meet it. Ground-based telescopes are getting more powerful. The Extremely Large Telescope, ELT, in Chile, with its 39-meter mirror, will be able to study interstellar objects in unprecedented detail. It could potentially resolve the nucleus of an object like 3I Atlas, seeing surface features that are currently invisible. New space telescopes are being planned that could detect interstellar objects farther out, giving us more advanced warning. Currently, we discover these objects when they're already relatively close to the Sun, often just a few AU away. But if we could detect them when they're still 10 or 20 AU out, we'd have years to study them as they approach, rather than just months. And as our detection capabilities improve, we might find objects that challenge our understanding even more than Oumuamua or 3I Atlas. Perhaps we'll find an interstellar asteroid that's clearly metallic, a chunk of the core of a destroyed protoplanet. Perhaps we'll find an interstellar object that shows unmistakable signs of artificial modification, though I, like most scientists, think this is unlikely. Perhaps we'll find one that's captured into a stable orbit around the Sun. becoming a permanent resident of our solar system. Let me end by talking about why this matters on a human level, beyond just the science. When 3I Atlas was discovered, it made headlines around the world. People who normally don't pay attention to astronomy were suddenly interested. Kim Kardashian tweeted about it. Joe Rogan discussed it on his podcast. It became part of popular culture. Why? I think it's because interstellar objects tap into something deep in human psychology. They're visitors from beyond, strangers from distant realms. They connect us to the vastness of space and time. They make the abstract concept of other planetary systems suddenly concrete and real. For most people, exoplanets are just numbers and statistics, masses, radii, orbital periods. But an interstellar visitor is different. It's here, in our solar system, something we can see through telescopes. It's tangible in a way that distant exoplanets aren't. And the mystery around objects like 3I Atlas, the debates about whether they're natural or artificial, the strange properties that don't quite fit expectations, these engage people's imagination. They remind us that despite all our scientific progress, the universe still holds surprises. We don't have all the answers. We're still explorers discovering new things. This is important. In an age when science literacy is declining in many countries, when conspiracy theories spread faster than facts, when political polarization makes it hard to agree on basic truths, space exploration and discovery can be a unifying force. Everyone, regardless of political affiliation or cultural background, can appreciate the beauty of a comet from another star system. Everyone can be excited by the possibility of learning something new about the cosmos. 3I Atlas, whatever it turns out to be, has gotten people talking about science. It's inspired people to learn about orbital mechanics, spectroscopy, planet formation, and galactic dynamics. It's reminded us that we live in a vast, ancient, complex universe that rewards curiosity and careful study, and that, perhaps, is its greatest contribution. I have to admit, working on this video has been a journey for me. When I first started researching 3I Atlas, I expected a straightforward story about an interstellar comet. But the deeper I dug, the more layers I found. The chemistry story leads to questions about planet formation. The planet formation story leads to questions about stellar populations and galactic evolution. The galactic evolution story connects to the origin of the elements and the history of the universe. Everything connects to everything else. That's what I love about astronomy. You start with a question about one object, and you end up learning about the entire cosmos. A single comet teaches you about the galaxy, and the controversy around 3I Atlas has been fascinating to watch unfold in real time. I've read dozens of scientific papers, preprints, blog posts, and social media discussions. I've seen scientists disagree passionately while remaining respectful. I've seen how the scientific process works when confronted with something unusual. What strikes me most is the intellectual honesty. When scientists say, "we don't know," they really mean it. They're not hiding anything or covering up conspiracies. They're simply acknowledging the limits of current understanding and the need for more data. That's refreshing in a world where everyone seems certain about everything. This video will need an update in a few weeks. When the December observations come in, we'll have new data to analyze. The story will continue. If you want to follow along, I recommend checking these resources regularly. NASA's official 3I Atlas page at science.nasa.gov, the Minor Planet Center's database for updated orbital data, the skylive.com for current position and observing information, the virtualtelescope.com feed, Project for live viewing opportunities, rxiv.org for the latest scientific papers. Search for 3I Atlas, and if you're in the astronomy community, consider contributing observations. Even simple brightness measurements from amateur telescopes help scientists track the comet's activity. This is one of those rare cases where citizen scientists can make real contributions to professional research. 3I Atlas is, in the end, a comet. It's made of ice and rock and dust, just like comets in our own solar system. It follows the laws of physics, just like everything else in the universe. It's not magic, it's not a miracle, and it's probably not aliens. But it is special. It's special because it came from somewhere else. It's special because it carries information about a planetary system that formed billions of years ago around a star we'll probably never identify. It's special because its journey through our solar system is a brief moment in a story that spans eons. For a few months in 2025, this ancient wanderer visits our neighbourhood. It warms up in the sun's light for the first time in billions of years. Astronomers on one small blue planet point their instruments toward it and marvel at what they see. And then it departs, accelerating back toward escape velocity, heading back into the dark. It will pass through the outer solar system over the coming years, growing ever fainter and more distant. By 2030, it will be beyond Neptune. By 2040, it will be entering the region where the sun's gravity fades and the galaxy's influence begins. By 2100, it will be truly interstellar again. Just another tiny speck of ice and rock drifting through the void. Perhaps millions or billions of years from now, it will encounter another star system. Perhaps astronomers around that distant star will detect it and study it and wonder about where it came from. Perhaps they'll detect the traces of our observations, the radar signals we bounced off it, the laser measurements, the spacecraft that might someday visit it. Perhaps they'll know that long ago, this comet passed through a system with a yellow star and a blue planet where curious beings studied it and wondered, or perhaps not. Perhaps 3I Atlas will wander forever, alone, never again passing close enough to a star to be warmed, never again being seen by anyone or anything, just drifting silently through the galaxy until the stars themselves grow old and cold. Either way, for this brief moment, we had the privilege of seeing it. We were here when it passed through. We looked up, we observed, we learned, and we wondered. And in the meantime, I can't wait to see what else we can learn from this plucky interstellar traveller. It has come an awfully long way, beating the odds to reach us, and I'm sure it has plenty of cosmic secrets to spill before it fades from our view and returns to the eternal night between the stars. If you've made it this far, thank you, seriously. This has been a deep dive, over 2 hours of science, speculation, and story. The fact that you stuck with it tells me you're genuinely curious about the universe, and that's wonderful. Here's what I'd like you to do. Share this video, not because I need the views, though that's nice, but because understanding 3I Atlas requires cutting through a lot of noise. If you found this helpful, chances are others will too. Stay curious. The December observations will reveal new information. Stay tuned for updates. Follow the science as it develops in real time. Look up. Find 3I Atlas in the sky if you have access to a telescope, or just look at the stars. And remember that between those points of light invisible to our eyes, countless ancient comets are drifting through the darkness. Some are heading toward our solar system right now. We just haven't detected them yet. Support science. The research that revealed 3I Atlas's properties was funded by taxpayers through agencies like NASA, ESA, and national science foundations. Telescopes like Hubble and Webb exist because societies chose to build them. If you value this kind of knowledge, support funding for scientific research and education, think critically. When you see sensational headlines about aliens or conspiracies, remember what we discussed here. Ask for evidence. Look for primary sources. Check what actual experts are saying. Science isn't about believing, it's about understanding. This video was based on hundreds of scientific papers, press releases, and observations. Special acknowledgement to the Atlas team in Chile who discovered 3I Atlas, the thousands of astronomers worldwide who contributed observations, NASA, ESA, and other space agencies for making data publicly available, the planetary science community for their rigorous analysis and debate, the researchers whose names I've mentioned throughout, David Jewett, Jane Liu, Avi Loeb, Megan Schwamb, Rohan Rahatgaonkar, Thomas Pouzier, and many others. Science is collaborative. Every discovery builds on the work of thousands of people, most of whom never get public recognition. This video is my attempt to synthesize their work into a story that non-scientists can understand and appreciate. If you enjoyed this deep dive, let me know in the comments what other cosmic topics you'd like to see explored. I'm thinking about videos on the Vera Rubin Observatory and the revolution in time domain astronomy, the search for Planet 9 in the outer solar system, the weird physics of neutron stars, the James Webb Space Telescope's most surprising discoveries, the hunt for extraterrestrial intelligence, and the Fermi paradox. But I want to hear from you. What questions about the universe keep you up at night? To everyone who watched, commented, shared, or simply thought about 3-Eye Atlas after seeing this video, thank you. The universe is vast and strange and beautiful, and every person who takes time to learn about it makes the world a little bit better. The comet doesn't care that we're watching. It doesn't know we exist, but we care. We watch. We wonder. And that act of curiosity, that desire to understand something that has no practical benefit to our daily lives, that's what makes us human. 3-Eye Atlas will leave our solar system and return to the darkness. But the knowledge we gain from studying it will remain. It will be added to the great accumulated understanding of our species, passed down to future generations, used to inspire new discoveries and new questions. That's the real value of exploring these cosmic visitors. Not what they are, but what they teach us about ourselves. That we're a species that looks up, that asks questions, that isn't satisfied with simple answers, that craves understanding even when the subject is billions of years old and billions of miles away. So here's to 3-Eye Atlas, the ancient wanderer. Here's to the astronomers who study it. Here's to everyone watching who lets themselves be amazed by the cosmos. And here's to the next interstellar visitor, whoever and whatever it may be. We'll be watching. Clear skies, everyone.